Welcome back. In this video, we're going to solve the descent path general linear systems problem. We've been developing this over the last two videos. Recall the idea is that we're flying along in this Boeing 787. We start our landing process at 40,000 feet. We follow this beautiful cubic polynomial down to landing 400 miles away horizontally at 0 feet. And we said that that path we're going to model with a cubic polynomial. And the reason we did cubic was having to do with curvature. That cubic polynomial had this form, and we wanted to know what are the coefficients a0, a1, a2, and a3 necessary to produce the exact path that we're looking for. We then used some information, the fact that we started at 40,000 feet, the fact that we landed at 0 feet, the fact that when we started our landing process, we wanted to be moving horizontal. When we land, we want to be moving horizontal. We imposed some conditions on that. Those conditions came in 4 flavors. Each condition that we descended had a verbal description and then also an equation, and we ended up turning all of these conditions into a general linear systems problem. That general linear system problem took this form. The individual components in our coefficient matrix came from the x values of our modeling context, as well as from the behavior of our polynomials with respect to the variable x. The right-hand side vector came from the y values in our model, aka the output of our polynomial path model. And the unknown vector that we're searching for are actually the scaling coefficients that uniquely determine this polynomial. The only reason that this is unique is because this matrix is non-singular. We forced additional conditions on our problem in order to make that to be true. Recall back to the previous video, the entire idea that we had in solving a general linear systems problem was to multiply that linear systems problem on the left-hand side by a sequence of elementary matrices, shear, dilation, and transposition, in order to transform this into special form. In this specific example, the special form that we're going to look at is row echelon form. Let's go ahead and do that. Specifically, we're going to take our original linear system and multiply on the left by the appropriate matrices. Before I do this, I'm going to actually show how to use MATLAB or Octave in order to do these calculations so that I'm not having to do them in my head. So we're going to go ahead. This is the MATLAB command window. We're going to go ahead and store the matrix A seen right here. So I'm going to say that the first row is 1, 0, 0, 0. The second row we look like 1, 400, 400 squared, and 400 cubed. The third row is going to be 0, 1, 0, 0. And then the fourth row looks like it's going to be 0, 1, 800, and looks like 4 zeros there, right? That coefficient matrix is indeed the same coefficient matrix that I have there. Just go ahead and check. So now I'm going to store the right-hand side vector. So B is going to be a 4 by 1, and I have a 40,000 in the first. Second column is going to be 0, third column 0, fourth column. So rows are delimited. So the way that we tell each column in a row is just by space. And then if I want to go row by row, the way that I move down in the columns is to use a semicolon. We'll kind of see that. All right, so now I have my matrix A, I have my vector B. Notice though that row 1 and row 3 are really beautiful from the standpoint of elimination, and then these two rows are a little bit more interesting. So I'm going to make the proposal. Let's go ahead and permute the rows a little bit. Let's switch row 3 to row 2. Let's switch row 4 to row 3, and let's switch row 2 to row 4. In order to do this, we're going to multiply on the left-hand side. The reason I know I'm going to multiply on the left is because I'm doing it by rows. For more about that, go back and watch the videos on matrix multiplication that I post. In this situation, notice I want to pull row 3 to row 2. So here, I'm going to pull one copy of row 3 and put it in row 2. I'm going to pull row 4 to row 3. That's exactly what I've done. In position 3, I'm going to grab row 4. And then I'm going to take row 2 and put it down on the bottom. So the fourth row is going to pull a copy of row 2 and put it on the bottom. If I do that on the left-hand side, I should also do that same matrix on the right-hand side. Some of you astute viewers will be like, hey, Jeff, that's not a transposition matrix. That's right. It's a permutation matrix. But my claim, here's a challenge to you. Find the two transposition matrices that generate that permutation matrix by multiplication. Let's go ahead and store that matrix in MATLAB. So I'm going to call E1. So it's going to be 1, 0, 0, 0. The next thing is going to be 0, 0, 1, 0. The third row is going to be 0, 0, 0, 1, and the last row is going to be 0, 1, 0, 0. So let's go ahead and multiply E1 times A. Notice that the matrix that comes out of that indeed has that structure that I want. Another way to say that is when I do that multiplication, when I multiply E1 by A, I get this matrix out. And then the really nice thing about the right-hand side vector in this case is that it's kind of beautiful, isn't it? So we're going to go ahead and say, like, okay, when I do this multiplication, I get this equivalent system. Now the question is, well, how do we turn this thing into row echelon form? Here we said that we're going to use the diagonal element right here as a pivot position. Once we use that pivot position, just as we did in Gaussian elimination, we're going to try to cancel out this subdiagonal element. We know that we can do that using a shear matrix. Specifically, we take the value in entry 4(1), negative on the front, and divide by that entry. And we notice that that shear matrix, we'll call it E2. When I multiply by that shear matrix, the corresponding entry 4(1) should go to 0. Anything I do to the left-hand side, I should also do to the right-hand side. So I multiply now on the right-hand side by E2. Let's go ahead and store E2. In this case, I know that E2 is going to be basically the 4x4 identity matrix, but the major difference is that entry 4, 1 of E2 is going to be equal to -1. So now I see that E2 is the matrix that I want, and I know that E2 times E1 times A, the claim is the entry right in that entry 4(1) should be 0. On the right-hand side, I multiply E2 by E1. Notice that when I do that, I actually get a copy of 40,000 in the bottom. And the reason that is when I look at the inner product version of multiplication, so I take this thing and multiply there, the negative 40,000 goes down to the bottom there. And that results in a system where I have the coefficient matrix, the desired value that I wanted to zero out is now 0. And the right-hand side, I have an extra copy of negative 400,000 in the last entry. Now the question is, well, how do I cancel out the diagonal elements in row 2? In other words, I'm going to move to my next pivot position. I see my next pivot position is entry 2, 2. Now I'm going to go ahead and cancel out each of these subdiagonal elements individually with a different step. So the first one I'm going to do is the one right under the pivot. In order to do that, we're going to use a shear matrix. The specific shear matrix I'm going to use looks like this. So that would be S3, 2, -1. For those of you that did not take my class, please go back and watch the matrix multiplication lessons. There's some really good stuff in there. So let's go ahead and set E3 equal I. It's a 4x4 matrix, and then we're going to claim that the the third row, second column is going to get a -1 value, and then when I multiply the previous matrix that I had by E3, notice that the entry that I wanted indeed turned to 0. Of course, whatever I do to the left-hand side, I also do to the right-hand side, and now I get this equivalent system where the entry 4(1) is 0, the entry 3(2) is 0. I'm going to go ahead and zero out the entry 4(2). In order to do that, I'm going to use a different shear matrix. So my fourth elementary matrix operation, I go ahead and try to zero this out. The way that I do that is I take this entry, put a negative sign on top, and divide by the diagonal element. That is exactly this shear matrix. If I multiply this equation on the left by my matrix, I also have to multiply the same matrix on the right-hand side. Let's go ahead and store that shear matrix. So E4 is going to be a 4x4 identity matrix with the additional condition that entry, 4, 2 is going to be -400. So now let's go ahead and do that sequence of operations again. I've multiplied A by the sequence E4 times E3 times E2 times E1. Notice that indeed cancels out that sub-diagonal entry that I wanted to do. I do the same thing over to my vector B, and I produce this new equivalent equation where I've taken A and multiplied by my sequence of 4 elementary matrices thus far. Now that I've canceled out everything under pivot 1, here was pivot 1, pivot 2, the next thing I'm going to do is choose pivot 3. I do want to say that there is something called diagonal dominance that comes up in numerical linear algebra. We are not to that. This is an introductory course. In reality, I should probably put the 1600 there. That has to do with how round-off properties work. But because it's an introductory course, I'm going to keep it real easy. You could actually do this example by hand if you wanted to. It's one of the reasons that I kind of chose the context that I did. So from that standpoint, we're going to go ahead and let 3, 3 be our pivot, and we're going to try to zero this thing out. Remember, to do that, we're going to multiply on the left by a shear matrix. In order to figure out which non-diagonal entry is going to be non-zero, it's going to be in position 4, 3, and then we're going to take this value, put a negative sign on it, and divide by 800. And if we do that, 160,000 divided by 800 is 200 with a negative sign. Here is my last elementary matrix required to zero out the subdiagonal elements. If I multiply on the left-hand side of my equation by that matrix, I must also do the same thing on the right-hand side. Let's go ahead and store that matrix in MATLAB. So E5 is going to be a 4 by 4 matrix. And then the entry in 4, 3 we said was going to be equal to 200. And then when I multiply this new shear matrix on that chain of elementary matrices, notice that I indeed cancel out that last non-zero. We can do the same thing for B, and this produces a upper triangular matrix U where all subdiagonal elements are 0. This is the exact stair step that I want. In other words, this is row echelon form. Moreover, we know it's not reduced row echelon form because some of my pivots are non-1, or some of the leading entries are not exactly equal to 1. And then, of course, here, this leading entry has a non-zero above it. The right-hand side vector we're going to call y. So in other words, we can actually go back to MATLAB and go ahead and say, like, hey, that chain, we're going to call that u. And then we're going to call y the chain of elementary matrices multiplied by the vector b. And if we go back and look at how we did backward substitution, we can literally solve for this by taking that last row first, divide this entry by that would give me my A3. Then I can move up backward. So if we do that, the nice thing is MATLAB automatically allows us to solve for that. Check that out. Let's go ahead and format long. I'm going to claim that I've actually done this by hand. You can actually go back to the lesson on backward substitution if you want a reminder. But when I solve this system using backward substitution, I produce the following value of x. Here's the by hand calculations. Here's the decimal approximations to that, which you see on screen as well in the MATLAB. And then this yields the polynomial p of x is 40,000 minus 0.75 x squared plus 0.00125 x cubed. In other words, when I look at this descent path, the polynomial equation that defines that cubic is given by this function with these set of coefficients, and those coefficients came from solving our original linear systems problems, but we didn't work with them in this form because the actual algebra of this is really, really messy. Instead, what we did is we took our original modeling coefficient matrices, applied a sequence of elementary transformation to change this to make it much more algebraically easy to find our unknown vector. This is a theme that we've seen in the non-singular linear systems problems. Now it's arising again. Let's go on to our second example, another real-world context, where we see an under-constrained system. So less equations that we have unknowns, and let's put that in row echelon form to see what it looks like when we don't have a square matrix at the start. See you in the next video.